Hey there, I'm going to talk about physiography of flowing waters. There's a lot to talk about, everything about streams in one day. So we'll just try, we'll do our best, take breaks when you need to, and here we go. So the Wild and Scenic Rivers designation protects our river's outstandingly remarkable values, wildlife, recreation, fisheries, cultural values, and free-flowing character. And it was established, the Wild and Scenic Rivers Act was established in 1968. I just wanted to give you some update on something nearby, is that the Wild Olympics, which designates all of these wild and scenic sections inside Olympic National Park, was passed in July of this year. So very exciting news about protecting rivers in our neck of the woods. So you can be a river scientist in a lot of different ways. You can be a geomorphologist and study rivers and their channel and basically just like how the water forms and flows and how it shapes the channel. You could be a hydrologist, and then you'd be interested in the water itself and precipitation and groundwater input, surface flow, and the connections between all of those things. Or you could be an ecologist, and you might study how the physical processes that geomorphologists and hydrologists study influence organisms, and then how those organisms that live in rivers influence one another. So you kind of need to know a little bit about all of these things, and so that's what we're going to talk about in this program. So as an introduction to what are called fluvial ecosystems, a lot of people might ask, what's the difference between a river, a stream, a brook, a creek, and a creek? Well, other than a general decrease in size moving down that list, there are no standard distinctions. And so we rely on kind of regional dialect. Around here, we call things streams or creeks. In other parts of the world, they might be called brooks or creeks or arroyos or other words. There's lots of really cool words out there for rivers. There are some really big rivers like the Mekong, the Mississippi, and the Amazon River. These are rivers in a class of their own. The largest river on Earth is the Amazon. The Mekong is a really interesting river. It's number 11. Mississippi is number 9. The majority of river length, however, is made up of small streams, what are called headwater streams, the very tippy top of the watershed. And so here is a table that shows river channel variation. And I'll go through this table a few times. But the first thing is that first order streams, or the smallest, littlest headwater stream, you add them up, there are the most of them. They are the shortest though, but if you add up their total length, they make up the largest total length of stream channels on Earth. But they're draining small areas, each one. Here's kind of a stream order, and what you see is that the headwater streams are the fingertips or the branch tips of this branching dendritic drainage pattern. And rivers and streams are tree-shaped generally. There are some differences though, depending on the geology of the landscape. And the smallest permanently flowing stream is called a first order stream or a headwater stream. When two first order streams come together, they produce a second order stream. So in terms of watershed math, 1 + 1 = 2. Easy, right? Makes sense. But what happens when two second order streams come together? 2 + 2 should equal what? 4? But no, in terms of watershed math, 2 + 2 = 3. So you only get to jump from a second order stream to a third order stream when something as big as you comes into confluence with you. So here's a stream ordering diagram. You might want to spend some time looking at this so that you understand how it works. You can see lots of places where ones and ones come together to make a 2. And then you can see places where 2s and 2s come together to make a 3. And then again, you have a 3 here, but another 2 coming in doesn't bump the 3 up to a 4. Another 1 coming in won't bump that into a 4. You only get a 4 when you have 2 3s coming together. And then downstream of 2 third order streams, you get a 4. So in terms of watershed math, we have 1 + 1 = 2. 2 + 1 still equals 2, but 2 + 2 = 3. 5 + 4 would still equal 5, but 5 + 5 would equal 6. So watershed math is not like regular math, and this is based on Strehler's stream order method. Here you can see the stream order going from 1 to 10. And there's only one 10th order stream in the world. Or sorry, this is the US, actually, US. So there's only one 10th order stream in the US, that's the Mississippi River, and it is in the top 15 in the world. But you can see that the drainage, so the number of these streams decreases dramatically as their length increases dramatically. The total length of these streams decreases, but the total area that they drain increases. So there's some really cool patterns in this table. And 50% of the world's rivers are intermittent or go dry. So there's kind of a big blank box here. Those brown arroyos that dry up sometimes of the year are not even really included in this table. So that's kind of a problem. So not all fluvial patterns are dendritic. You can see, depending on the geology, you can see radial patterns around mountaintops, annular patterns, trellis patterns where you have kind of cracking of the Earth's surface, contorted patterns, maybe where you have a lot of metamorphic rock. So lots of different types of patterns. A lot of these patterns are fractal patterns, though. They're self-repeating patterns. So there's a lot of what's called fractal architecture in river patterns on Earth. Now the terms basin and watershed are similar to the terms river and stream. There are no strict guidelines for when to use the word basin and when to use the word watershed. Drainage basin and river basin tend to be applied to larger units, whereas watershed and catchment tend to be applied to smaller units. And sometimes there are differences across the pond, right? So the US uses some terms like watershed, whereas in Britain you might use the word catchment. So there are some differences regionally like that too. This is what's called a storm hydrograph, and it shows how you have flow through time. And base flow is kind of what's the steady flow of a river, kind of its normal flow. But if you have some intense rainfall, and blue is showing the rainfall, as the rainfall happens, then the stream starts to flood. And there's a lag between the peak precipitation and the peak storm flow, or the peak stream flow. That's called the lag time. And you can also see this time of rise, and then you see a recession limb as the storm flow drops off. So a hydrograph shows you, in this case, how long a stream takes to rise from base flow to maximum discharge and then return. But you can also look at hydrographs over longer periods of time. So in panel A, you can see a hydrograph that goes over many, many decades. And it shows you variation in stream flow discharge, which is how much water is flowing out of a stream for a spring-fed stream. So you can see it's relatively steady, but it oscillates around a mean. And then in B, you can see what a spring-fed stream hydrograph would look like for just 1 year. And so you can see, again, there's a lot of steadiness and some oscillating around the mean. Panel C shows you what an intermittent stream might look like through time. And so there are peaks, and then there are troughs where it goes dry, and then it peaks again and troughs. And so you can see those patterns through time. In D, it shows you an intermittent stream over just 1 year. So it shows you the peaks when the water is flowing, and then it dries up, and then another storm happens, and it dries up. And then panel E shows you a rainstorm fed stream. So a lot more variation around the mean when a stream is relying on rain versus spring fed streams. So lots of really cool patterns we can see in hydrographs. There's a couple more, the top showing again that rainfall discharge pattern, but the bottom showing you that if you're a stream that has been urbanized, that your peak in terms of flow is going to be higher, and the lag time is going to be slower. So urbanization causes quicker, higher peaks in floods, which is a problem for people. Other thing that we can see is that dams decrease variation. So here's a picture of the Upper Missouri River from Scalak et al. 2006, showing in blue the pre-dam hydrograph through time. So lots of peak flows, spring snowmelt flows, and then some summer rainfall flows. And then in 2011, after they put in a dam, you can see that the flows change. They're releasing water, it looks like, in the summertime. And then the rest of the hydrograph is pretty flat on either side. So humans alter stream flows. We change flows, we channelize rivers. We like to build in floodplains and dam rivers, and we like to pull water out of rivers. All of these things tend to reduce the variation around the mean, and they reduce the dynamic nature that is crucial to how river ecosystems work. So in a sense, one of the biggest problems, one of the biggest disturbances to rivers is the lack of disturbance. Okay, so the lack of variation in flow ends up being one of the major disturbances in rivers. Okay, we're going to take a little break and come back.